This week we look at metrics. Predictive models don't make assumptions. We don't derive predictive models, that is. So it's crucial that we measure their performance rigorously. We're going to start out with some basic metrics: false positives, false negatives, the confusion matrix. And we're going to learn that it's important to measure rates of false positive and false negative. So what did we look at last time? We saw a decision tree classifier, and it predicted who was going to get dessert. But how good is it at predicting if someone's actually going to get dessert? In the data set, for example, there are 2 adult women who drink tea, do not get an appetizer, do get a salad, and do order the chicken. One gets dessert and the other doesn't. We also looked at predicting the desirability of an automobile. We used a decision tree classifier last time. But how good is it at predicting if somebody's going to rate a given car very good based on the features that car has? That is, if we've got an observation, an unclassified observation, and we know what the features are, but we don't know what class it's in, can we use the decision tree to reliably predict whether or not that will be a person who rates the car as a very good buy or not? So we've got 2 binary classifiers, 2 decision trees. Do either of them work? Do neither of them work? Does one work and the other doesn't? And so, how can we tell? So a binary classifier is trained by data. It's going to have p positives and n negatives. The number of actual positives p and the actual negatives n. This typically is not all that useful. We do often assume that the ratio of p to n is approximately the same in the real world as it is for the data we've collected, but typically we have no real reason to make such an assumption. Now, what does a classifier do? It labels observations as either being positive or negative. Small p is the number that are labeled positive, and small n are the ones that are labeled negative. The ratio of p to n is often interpreted to be a property of the classifier. So if we took the same classifier and applied it to a data set that's twice as large, then about 2p and 2n observations will be labeled as positive and negative, respectively. We're not assuming that has to be true, but that tends to be the way it works out. Now, using the p positives and n negatives, we use metrics to measure the performance of a classifier. So what is a metric? A metric is a measure that we can analyze and control without prior assumptions about the data. So metrics can relate a classifier to the process that produces the data without relying on the data itself. So a metric, unlike with a descriptive model where you estimate parameters and find confidence intervals and that sort of thing, a predictive model doesn't have those features, and so instead what you do is you use a metric, and a metric is used to relate what the classifier is predicting to what the process that produced the data is all about. And metrics can actually tell us if a given set of data is capable of answering the question that we're asking. Or, perhaps more importantly, metrics can be used to reject a predictive model. Of course, nothing can force us to accept a model. We're going to start with the confusion matrix. The confusion matrix is based on the idea that there are 4 possible outcomes of a binary classifier: true positives and true negatives, false positives, observations that are actually negative but the classifier said they're positive, and false negatives, positive observations that the classifier labels as negative. So we recall these definitions. And the confusion matrix we write in this way: the notation TP, FP, TN, FN. We tend to put these in a table where we have the predicteds across the top and the actuals down the sides. And the true negative plus the false negatives will give us the number that are predicted negative. And the true positives plus the false positives will give us the number that are predicted positive. And going the other way, of course, we'll get the positives and negatives, the capital N and capital P. So let's look at an example. Who's getting dessert? Here are the actual raw numbers. So we have 76 total negatives and 35 positives, and you see there the breakdown in numbers. And so we have true negative of 70, a true positive of 9, false positive 6, and false negative of 26. It's a lot of false negatives, you might notice already. Now let's compare that to the question, should I buy this car? In other words, the rating as very good. So notice now the false positives and false negatives are relatively small compared to the true positives and true negatives. So let's look at this in terms of accuracy and error. So the error is the number of falsely predicted observations over the total number of observations. And for us, that's false positive, false negative is 28.8%. So for the dessert data, notice we can actually write instead of the, and let me back up and show you that again. So notice we've got 70 here, and we can write that as a percentage of the total, and the false positives and false negatives and the true positives as percentages also, and that gives us essentially something that's on the same basis as the overall error. Same thing with the should I buy this car. The overall error is only 7 over 70/28, only 0.4%. That's a very low error. And again, we can look at the confusion matrix in terms of percentages. Now accuracy is the rate of true positives and true negatives to the total, and that's 71.2% for the dessert and 99.6% for should I buy this car. So how do we deal with all these numbers? We see that they're useful. We can convert them into percents. And in general, we tend to use these as ratios such as the true positive rate, which is true positives over the number of positives. So we call this sensitivity or recall. Both names are used. We'll see that later. And then the false positive rate is the number of false positives over the actual number of negatives. So let's look at who's getting dessert. The true positive rate is 9 over 35, and that's 0.257. The false positive rate is 6 over 76, which is 0.0789. Now what do these mean? Well, we'll get to that in a minute. But let's look at the same numbers for should I buy this car. So the true positive rate's 0.938, about 94%, and the false positive rate very close to 0. Now ideally, if we had a perfect classifier, the number of true negatives would be equal to the number of negatives, the true positives would be the positives, and we would have no false positives or false negatives. But in reality, the true negatives are hopefully the same as the negatives minus epsilon, some small epsilon. And the same thing with the true positives. Hopefully we're only off by some small delta from the actual positives. And hopefully epsilon and delta are small. Now assuming that the epsilon and delta here are small, notice the true positive rate is mathematically reduces to 1 minus delta over p, and if delta is small, then that's approximately 1. And notice if it's delta here has to be small with respect to capital P. The false positive rate, epsilon has to be small with respect to capital N in order for it to be approximately 0. So notice again we have the true positive rate, ideally it should be close to 1, and the false positive rate, ideally close to 0. So you can see actually we have pretty good false positive rates in both of these, but the true positive rates are another story. Who's getting dessert has a very low true positive rate. Now let's go back to reality. So we've got the true positive rate is approximately 1 and the false positive rate is approximately 0. But notice that we could have a situation where epsilon was, say, small with respect to capital N but large with respect to capital P. So we actually need the actual row negatives. So the actual negatives, we need to also relate those to the actual positives. And to do that, we're going to need more metrics. So let's look at this put all together. We're going to have statistics that are derived from the confusion matrix. And we say stats, but we're just looking at basic metrics here. So the specificity is true negatives over true positives plus false negatives. Sensitivity and recall looks like that. Accuracy, we've seen that already. Precision, true positive over true positive plus false positives. And we're not going to use it very much, but the NPV is the negative predictive value. So let's look at sensitivity and recall. The true positive rate is the sensitivity of the classifier. It's an estimate of the probability that a positive observation will be classified as positive. And so high sensitivity means a low likelihood of missing an observation in the positive class. Now, the true positive rate is also known as recall in the sense that you can think of it as the fraction of those that are positive that we actually recalled as actually being positive. Specificity is for the negatives, what sensitivity is for the positives. And the reason we have different terminologies is because this is related to the concept that our goal is to identify the positives. Positive for a disease, for example. So the idea is that there's a different impact for something being positive as being negative. So high specificity implies a classifier that rarely misses negative outcomes. So that means that prediction of positive is highly reliable. So think in terms of a disease. If a test comes back positive for something and it's highly specific, then you're pretty confident you have the disease. Now, specificity in the false positive rate. So capital N is the false positives plus the true negatives, because the false positives are actually negative. The specificity is Tn over N, which is Tn over Fp plus Tn. And we can write that as Fp plus Tn over Fp plus Tn minus Fp over Fp plus Tn. A little bit of algebraic manipulation here, but notice the Fp's would cancel out in that last expression. And so the specificity is 1 minus Fp over N, or 1 minus the false positive rate, which means the false positive rate is 1 minus the specificity. So let's go back to dessert. Go back to our examples. So for the who's getting dessert, we had a true positive rate of 0.257, so that's also our sensitivity. And likewise for the car, sensitivity of 0.938. The specificity is 1 minus the false positive rate, so we subtract each of those from 1, we get a specificity of 0.9211 for the who's getting dessert, and 0.98982 for should I buy this car. Another important measure is precision. Precision is the fraction of observations classified as positives that are actually positive. So, and we're going to compare this to recall. Let's look at some examples here. So now we're going to call the true positive rates recall. So we saw that was another word for sensitivity. The precision for the who's getting dessert is 0.6 out of a possible 1. And whereas for the should I buy this car, the precision 0.953. And we'll talk more about precision and recall later on. But for right now, remember that our goal was to somehow be able to relate the epsilon and the delta. So let's do this little calculation. The precision is true positive over true positive plus false positive. Let's divide throughout by the true positives. And putting back in our numbers, you can see those in the table up there. The true positive is p minus delta in reality, and the false positive is epsilon in reality. And so notice the precision has the epsilon and the delta both inside of the expression. What does this mean? Well, it means we could only get a precision of 1 if both the epsilon and the delta are small relative to p. So to summarize, sensitivity equals recall equals true positive rate. We also have the false positive rate, specificity, precision, recall, and of course there was also error and accuracy and some other things as well. Avoiding a train wreck. We've been looking at decision trees, but decision trees have many shortcomings. We also have another classifier, if you remember, and that's the k nearest neighbors. But in both of these, we have to worry about overfitting. And so to deal with overfitting and the problem of false positives and false negatives, we need to use what are called validation and testing to avoid a training wreck, if you want to think of it that way. So remember from last lecture, we looked at these two examples. Who's getting dessert? Should I buy this car? We had true positive rate, false positive rate, as you see down there. But this was only for the training set. So let's suppose we include validation and testing. So what do we mean by that? Well, let's just recall, we've already talked about this a little bit, but remember we can take a set of data and we can break it into 3 parts. And a lot of times we take, for the actual design of a classifier, an entire training set itself, and we might break it into 3 parts. The training set to build the classifier, the validation set that's used to tune or test the classifier as it's being constructed, and finally the test set, which is used to actually determine how well a classifier performs. So we design based on the training set, tune based on the validation set, but we accept or reject whether or not we should use such a classifier based on the test set. Now, for example, let's suppose we chose 20% as a test set. So 80% of the data is going to be used for training and 20% for testing. So here we have our confusion matrix for the car and for the dessert. And notice that for the should I buy this car, it looks pretty good. For who's getting dessert, well, not so great, but you know, let's see what we get. So for who's getting dessert, we have a true positive rate of 0.111 and a false positive rate of 0.133, and the first should be close to 1 and it's not, and the second should be close to 0 and it's really not. In contrast, let's look at should I buy this car. The true positive rate is 0.857. It's not terrible. And the false positive rate is 0 here. Well, that's because you can get. Now let's notice something else. The dessert data, when we partition it into 80% training and 20% testing, we actually wind up with a different tree classifier. So here's the same data set with 100% of the data compared to the decision tree we get with 80% of the data. And notice I'm using the new rattled way of drawing decision trees to better illustrate what's going on here. Let's suppose we randomly selected another 80% from the training set. Then with 100% of the data, we have that. And now we have, with a different random selection of 80% to be the training set, we get an entirely different decision tree. And we do it again, yet another kind of decision tree. However, if we look at the car evaluation data, when we partition it into 80% training and 20% testing, the classifier that we get from the training data is about the same as we got when we used the entire set of data. So here's with 100% of the training set as compared to with 80% of the training set. So pretty close. Measuring on test sets in particular allows us to reject poorly performing classifiers. And the reason we have to do this is we have to remember that big data is cursed. Classifiers always produce results. It doesn't matter. It doesn't matter if we have a good classifier or not. It's going to classify into either class 1 or class 0. So that means that metrics allow us to reject poor performers, and that means we have to differentiate between making an algorithm work and measuring an algorithm's performance. So two entirely different ideas.